Welcome to Chemical Process Safety. In the last video, I introduced the idea of flammability limits, which dictate the lower flammability limit and the upper flammability limit, given the variable names LFL and UFL for us. This one's our favorite, by the way, being at the University of Florida. Everybody loves the UFL who's a Gator. Starting off by talking just about what it means, and just to reiterate, below the LFL, there's not enough fuel, and above the UFL, there's not enough oxygen. So right in the middle, where there's a good mix of fuel and oxygen, you have an ignition. So this is just a quick plot just to illustrate the point that these were discovered by people doing experiments. So imagine some poor grad student in a lab all day who was charging different compositions of fuel and air into a combustion chamber and trying to light it and see if it ignites. Obviously, the better mix you have, the more pressure that you've got. There's some interesting science related to how carburetors work. But for our purposes, any explosion is going to be dangerous. Doesn't matter necessarily what the maximum pressure that you get out of that explosion is. So these have been studied for a variety of fuels, by the way, of pure fuels. And if you ever need to know the LFL or the UFL, which you definitely will, you can find that data in table AB1. A slightly more complicated case is, what if you have a mixture of fuels? Oh, and before I move on, I should also say the LFL and the UFL are defined for the fuel being mixed with air. And for this class, just as in MEB, I will specifically constrain. When I say air, I mean a mixture of 79% nitrogen, 21% oxygen. So if I have a mixture of fuel and air, it doesn't necessarily mean I have 79% nitrogen, 21% oxygen. It just means that the proportion of nitrogen to oxygen is always 3.76, which is 0.79 divided by 0.21. So that's important because when we get to chapter 7, which is about inerting, we're going to start taking oxygen out of the air. That is going to change the LFLs and the UFLs if the proportion of oxygen and nitrogen is different. But anyway, we've got these formulas that are available in your book to calculate what the LFL for a mixture of fuels is. This is basically just a weighted average. So what you do is you take YI, and we'll define that here to be the mole fraction on a combustible only basis. So let's just say I have an example down here, which we'll get to that. But this is not the actual mole fraction. This is just the mole fraction if you remove everything that's not condensable. So you take that mole fraction, you divide it by the LFL of that mixture, you plug it into this formula, that gives you your LFL of the mixture. Also be aware of the decimal points. This book is very weird about how it defines it, but I like to think about, or I always say, compositions are decimals. But in this formula, and in a lot of the formulas in this chapter, they will report the LFLs as percentages, and they'll plug those in. So for example, if the LFL was 3%, you would plug the number 3 into this formula as opposed to 0.03, which makes intuitive sense to me. But anyway, that's how the book does it. Let's look at this quick example here. Let's say we had a mixture that was composed of 0.8% hexane, 2% methane, and 3% ethylene. And our question is this mixture flammable? So in order to know the answer to that, we have to calculate what the LFL for the mixture is and what the UFL for the mixture is. So I'm given actual compositions here. So what I first have to do is convert that to a combustible only basis. So what I'm doing here is I'm summing up the compositions. I'm summing up the percentages. So we have total of 3.3% combustibles, and the other 96.7% would be just air. 0.8 divided by 3.3 is 24%. So that becomes our Y for hexane, which we'll plug into the formula. 61% for methane. If you take 2 divided by 3.3 and 0.5 divided by 3.3 is 15%. I'm going to obtain the LFLs and the UFLs from table AB1. So check in your book and make sure that you get the same LFLs and UFLs. I get 1.2 for hexane, 5 for methane, and 2.7 for ethylene for the LFL. For the UFL, I get 7.5, 15, and 36 respectively. So crunching the numbers here, The LFL that I get is 2.65. And important to note here that the LFL for the mixture is not necessarily the same as the LFLs for any of the individual components. So it's affected by what the relative proportions of these fuels are. The LFL is 13% when I plug it into this formula. And from this, we would conclude that because I already know that the total mole fraction is 3.3%, that is between the LFL of 2.65 and 13, which is the UFL. Therefore, we would conclude that this mixture is flammable and therefore represents a fire hazard if we don't go through the trouble of inerting that vessel. And complicating things just a little bit, when you look up the LFL and the UFL in the back of the book, it is going to report the LFL and the UFL for a temperature of 25 degrees Celsius and a pressure of 1 atmosphere. However, the LFL and the UFL are actually functions of temperature, and these equations are in the book, and they describe what the dependence of the LFL and the UFL are on temperature. So in a majority of situations and cases, the temperature in your chemical plant is probably not going to be all that different from 25C. Even if you have process units that operate at higher temperatures, oftentimes those are temperature controlled or insulated or things like that. So even if you did have a release and you were to theoretically have combustion occurring, it would be at a temperature that's close-ish to 25. So you probably won't have to worry about this too often. But it's here just to make sure if you had a different temperature. I have an example here, but I won't go through it just in the interest of time. If you had a very hot part of the process where it was 150 degrees instead of 25, you would find that the LFL would decrease to 2.72% instead of 3%. Pressure is also something that could theoretically change the LFL and the UFL. The LFL is not super sensitive to pressure, but the UFL is. So again, there's an equation in the book that would tell you how to treat this, and I'll just direct you to that equation and use it if you see fit. There are rare cases where the chemical that you need is not listed in table AB1, and in this situation, what you could do is estimate the LFL and the UFL according to these equations. So LFL is equal to 0.55 times CST. This stands for stoichiometric concentration, which we'll talk about in just a second. I want to be clear that you should not use these equations, either one, if you have access to actual data. Actual data is always going to be better than these equations, and you should not use these equations if you could just simply look it up. All right, what is this CST business? Let's talk about that quickly. First, let's consider the combustion equation for just a generic fuel. This is something that I covered back in MEB. You might remember this. If we had a hydrocarbon fuel that could potentially have some oxygens in it, we'll call the number of carbon atoms in the fuel molecule M, the number of hydrogen atoms in the fuel molecule X, and the number of oxygen atoms in the fuel molecule Y. And then Z is the stoichiometric coefficient for oxygen. That is going to give rise to M molecules of CO2 because the carbons have to balance in the balanced stoichiometric equation. And we'll have X by 2 molecules of hydrogen. So you can see if I balance this equation, I'm going to have X divided by 2 times 2 hydrogens on the right, X hydrogens on the left. If I work out what the value of Z is, this is an instructive thing that I would like to do in MEB, but this, I like to have students practice balancing the equations by themselves. But you can prove by rearranging the equation that Z is going to be equal to M plus X by 4 minus Y times 2. I encourage you to try this out and make sure that you agree with this formula. And C stoichiometric is going to be defined as the number of moles of fuel divided by the moles of fuel plus the moles of air, and that's a percentage, so multiplied by 100. Where the number of moles of air is Z, the stoichiometric coefficient, divided by 0.21, and that comes about because air is 21%. Maybe a little bit confusing, so perhaps it would be helpful to look at an example. So let's look at propane for that example. Propane has the molecular formula of C3H8. That's going to give us 3 carbons on this side, 4 waters on that side. And by using my Z equation or just by balancing the reaction, I get 7/2 for Z. So the question that we might ask is, how much air do we need in order to combust 1 mole of propane? So because I need 7/2 or 3.5 times as much oxygen as propane, the answer is 3.5 moles of oxygen. But remember that this only composes 21% of air. So if I account for that and I divide 3.5 by 0.21, I get 16.66. And to be clear, there's many other ways that I can do this. What the way that I prefer to do this calculation is first by figuring out how many moles of oxygen you need, and then 3.76 is the number that I like to use. If you multiply the number of moles of oxygen by 3.76, you get the moles of nitrogen, and then you could add those two together to get 16.66. That is a slightly more complicated way to calculate it, but it's a way that makes more logical, intuitive sense to me rather than just dividing by 0.21. But both will get you to the same place in the end. The mole fraction of propane then is going to be 1 divided by 17.66, and that is because I'm adding 1 because that's how many propane we had, and dividing it by 17.66, that's 16.66 moles of air plus the 1 mole of propane, and that gets me 5.66%. That is what C stoichiometric is for propane. And let's just say we were living in a universe where nobody had studied propane. Obviously, that's not true for our universe. But if I didn't know what propane's LFL and UFL were, and I wanted to estimate it, I would plug it into this equation. So I'd multiply 0.55 times the stoichiometric concentration. That would estimate the LFL for me. You can actually do that and plug it in and see how far off those estimates are. Let's introduce some other quantities that are of interest. In addition to the LFL and the UFL, we have the LOL and the UOL. These are acronyms that stand for the lower oxygen, the limiting oxygen limit. Wait, no, that's not true. Sorry, LOL is the lower oxygen limit and UOL is the upper oxygen limit. I apparently need some coffee this afternoon. This is the concentration in pure oxygen that will burn. And the UOL is the concentration in pure oxygen that will burn as well. Now, you might wonder why there's all these different definitions kind of going all over the place. And that is because all these properties are going to be useful in constructing flammability diagrams, which is going to be the subject of the next video that I will talk about now. So I'm going to cut this video just to make sure I keep it manageable. And then we'll talk about flammability diagrams in the next video, keeping in mind that all these properties that we've discussed, LFL, UFL, UOL, LOL, and LOC, which I almost forgot, limiting oxygen concentration, are going to be useful. Most of these things, I'll also point out, there is a table either in the book or in the back of the book that you can go to look at that. All right, bye for now. See you next video.